given the following information for ether. So ether is a chemical substance that used to be used instead of anesthesia. We used ether to knock people out for undergoing surgery, but ether, which is C2H5O, C2H5, so it looks the same on both sides of the molecule. We have, here's our oxygen, and then we have hydrogens, and there are 5 hydrogens and 2 carbons on both sides. So it looks the same over here. So that is ether, and you didn't need to know that, but just for fun. So we want to calculate the amount of heat in kilojoules needed at 1 atmosphere to vaporize a 20.8 gram sample of liquid ether at the boiling point, so 34.6 degrees Celsius. So we are going from liquid ether to gaseous ether. We're vaporizing. All right. So do we need to worry about the heat of fusion at all? Are we anywhere near solid ether? No. Do we need to worry about the specific heat? Are we heating up our water at all? No. Sorry, ether, not water. We are just going from liquid to solid at 34.6 degrees Celsius. We don't need to heat up the liquid to get to that point. We are already at that boiling point. So all we need to know is our delta H of vaporization. So delta H of vaporization is given in units of kilojoules per mole. So 26.5 kilojoules per mole. So we need to know how many moles this sample is so that we can cancel out our moles and end up with just heat in kilojoules. All right, so how do we get the moles from the mass? The same way that we've been doing it for the last 2 chapters. So we have 20.8 grams of ether, and we are going to divide by our molar mass, which, if we look it up, is about 74 grams per mole. All right, so that's us moles of ether. And now to get our heat, we want to multiply by our delta H of vaporization. So 26.5 kilojoules per mole. So when we do this dimensional analysis, we're going to cancel out our grams, we're going to cancel out our moles, and our final answer is going to be in kilojoules, which is what the question asks for. So break out my calculator and do 20.8 times 26.5 divided by 74. And I got 7.45 kilojoules. So we need 7.45 kilojoules of energy to vaporize our liquid ether when we are at the boiling point. Great. So what about when we're not at the boiling point? So if we're not at the boiling point, we need to look at something called our heating curve. And we need to analyze the different stages of heating. So for this is the heating curve shown for both water, the orange line, and benzene, the blue line. And they're both 100 grams of sample. So when we start back here at negative 20 degrees Celsius and 0 kilojoules of heat added. So that's point A. Between point A and point B, we are increasing the temperature. The heat is warming the solid up to its melting point. The melting point is given by this line. So It's right at 0 for water and a little bit above 0 for benzene. So where the line goes horizontal is the melting point. So that first horizontal line is the melting point of the liquid. So from A to B, our temperature is increasing. As you can see, we don't have a horizontal line. We have a increase in temperature, an increase in the y-axis as well as the x-axis. But from B to C, that is where we have our horizontal line. So from B to C, the temperature doesn't change. So this is what we discussed for ice at 0 degrees Celsius and what we just looked at for ether at its vaporization point. So when you're at that phase change, the temperature doesn't change. Delta T is 0. There's no change in temperature. It's a horizontal line, and the solid is being transformed into a liquid at that melting point. Okay, so now we're going to look at C to D. So going from C to D, we see our temperature increase again. We're going back up, we see the y-axis. We see an increase in the y-axis as well as the x-axis. So temperature is increasing and the heat is being supplied. So we are warming the liquid to the boiling point. So that boiling point is what we hit at D. So our boiling point is a little lower for benzene than it is for water. So water is right at our 100 degrees Celsius where we'd expect it. Benzene is a bit lower at like 80. So that is our boiling point where it goes horizontal again. So now from D to E, we are converting from liquid to vapor. We are at our boiling point or our vaporization point. And the energy that's supplied is all delta H of vaporization. None of it is going into an increase in temperature. So the temperature, again, flattens out. We have a horizontal line, there's no increase in temperature because all of the energy is required for the vaporization and none is used for increasing the temperature. So down here from B to C was our delta H of fusion for going from solid to liquid. And then finally, from E to F, our heat is warming the vapor above the boiling point, and our temperature starts to go up again. So from this heating curve, we learn a lot about our substances. So we can see that the boiling point of benzene is lower in temperature than the water boiling point. But the fusion, the melting point of benzene was higher in temperature than the water boiling or water melting point. So we learned those two things. We also can learn about the delta H of vaporization and fusion. The delta H of fusion for water is a little bit bigger. The line is a little bit longer in the horizontal for water than for benzene. And the delta H of vaporization is a lot bigger for water than benzene. The horizontal line is a lot longer. You need to add a lot more heat before you can start increasing in temperature again. I know there's a lot going on here, but another thing that I want to show you guys is that, so the horizontal lines are boiling point and melting point, but these, not these, what could I call them? Where the line is increasing in both X and Y, that part of the line are the different phases. So this is the gas phase. This is the liquid phase. And down here is the solid phase. So between A and B, we're a solid. Between C and D, we're a liquid. And between E and F, and beyond F, we're a gas. So that's why you can see that the transition between B to C and D to E are our melting point and boiling point. It's where we go from our solid to our liquid and our liquid to our gas. All right, so let's see what we can do with all of this information in an example. All right, so the following information is given for benzene at 1 atmosphere. So first, we have a 45.20 gram sample of liquid benzene. It's initially at 49.3 degrees Celsius. So we don't need to build the melting point. We are already above the melting point, so we don't need to worry about solid benzene at all. All right, so now we're heating our sample at constant pressure and calculating the amount of energy needed to raise the temperature to 107 degrees Celsius. So that's all well and good. We could just calculate the difference between those two and use that as our delta T, but there's a problem with that. The problem is that in between those two temperatures, our benzene is going to boil. It's going to boil at 80.1 degrees Celsius. So step 1, we're going to heat liquid benzene from 49.3 degrees Celsius to the boiling point. Number 2, we have to add energy or heat to boil the benzene and get to gaseous benzene. And then number 3, after the boiling point, we need to heat our gaseous benzene to 107 degrees Celsius. So we have 3 steps in this problem. So if we drew it as a heating curve, we'd start by increasing the temperature, and this would be our liquid phase. Then we'd have to boil. This would be our boiling point. And then we'd heat our gas. All right, so step 1, how much energy do we need to heat liquid benzene from 49.3 degrees Celsius to 80.1 degrees Celsius? So that's where our specific heat is going to come in. The specific heat of liquid benzene is 1.740 joules per gram per degree Celsius. So our C equals 1.740 joules grams Celsius. And that's equal to Q. So Q is our heat that we want to find. We'll call that Q1, as this is only the first one we want. All right, and that is divided by the mass, which is 45.2 grams, times the change in temperature. So we're only talking about the change in temperature from the boiling point, so 80.1, from our initial temperature. So 80.1 minus our 49.3. Okay, so if we solve for Q1, we're going to multiply both sides by our mass and our temperature difference. So we're going to have 1.74 joules per gram degrees Celsius. We're going to multiply by our 45.2 gram sample, and we're also going to multiply by our temperature difference. So times parentheses 80.1 minus 49.3. All right, so that Q is going to be 2,422 joules. We got to know our units are joules. Okay, so there's one. So I'm going to write that up here so that we keep it in mind. So Q1 is 2,422 joules. All right, so now we're going to Q2. So Q2 is going to be the heat required to vaporize. So we want to look at delta H of vaporization. We're at 80.1 degrees Celsius. So it's going to be equal to 393.3 joules per gram. And we're going to multiply by our mass to cancel out our grams. So 45. I really want to write 42, but it's 45.2 grams. So grams cancel out. And the heat required to vaporize our benzene is 393.3 times 45.2, which is 17.777 joules. All right. So we've got 24, 22, and 17,777 so far. We need one more. So our Q1 was 24, 22. Our Q2 was 17,777 joules. All right, one more. So Q3, we're going to go above the boiling point. So when we're above the boiling point, we need to use the specific heat of our gas. So now instead of specific heat of liquid, we need the specific heat of the gas. So this is going to be the same we did as the first step, using a different specific heat. So for the gas, it's 1.040 joules per gram degrees Celsius. And it's still going to be equal to our heat. So this time it's Q3 over our mass, still the same mass, 45.2 grams. And our temperature difference this time is going to be from the boiling point to our final temperature. So 107 minus 80.1 degrees Celsius. All right. So again, we want to multiply our mass and temperature difference to the other side so that we get Q3 by itself. So 1.04 joules per gram per Celsius times 45.2 grams times parentheses 107 minus 80.1 is our temperature difference. And this time I got 1,265 joules. So our total amount of energy is going to be all three of these added together. So let's see. We need 24.2 plus 17,777 plus 1265. So total Q, total heat required is 21,464 joules. And if they want us to convert to kilojoules, we just divide by 1,000. We move our decimal place over 3 times. So 21.46 kilojoules. Because all of our given numbers had 4 significant figures, we want 4 significant figures in our answer.